Okay, I'm gonna record. I've hit record this time. Okay, okay. I promise you, we're gonna just get after this. Ready? So this is one collision. All right. Every collision, you get about a collision every 25 nanoseconds. And the question is, how do you even know there's a collision? So that's my goal for today. Is that okay? Okay, cool. We don't have a pear deck yet. And that's okay. I got you. We're gonna do some stuff later. We ended yesterday by looking at cloud chambers, and it's basically a way of visually seeing an invisible particle moving. Okay. I want to hit you with a couple ideas. There's really three. We're gonna hit a couple more. We're gonna hit four ways. But one way of knowing you have a particle is it heats something up. So you might have a small detector that actually notices an energy change, or it heats up, or it gets excited. Okay. The second is if you have something that's charged. That's really easy. What you do is you put it through a magnetic field and you bend it. That's one way. So then you know how much charge it is, and you can contain it. I mean, it's really cool. So now it doesn't hit your other detectors. When these collisions happen, they make it so all the electrons that come off are localized. And so they don't actually go outwards into the detector very far, which is pretty cool. But the big ones like muons or taus will just go flying through them, and they'll just whoop, off they go. They'll go right through. You can try to stop them, but they're too heavy and too much energy. And so one of the things we do is we can have it hit something and measure a current, because a muon and an electron, they're charged. So we can have a wire go, hey, there was a current here. And so we can then go, okay, well, right here at this spot right there, I measured a current. That means that there's a charge there. Okay. How do you measure a current? Well, radios, like a radio antenna, that's one way to measure current. If you have a moving current, it makes a sound because it causes a magnetic field. That's the best example I got. That was kind of lame though. This last one is a word. I want one of you to try to say it. Crowd participation.
Scintillation.
Yeah, nice job. What it means is you excite something and light comes out of it. And so these are actually really cool little things. We're going to talk about how they do it. If you have a little piece of glass and it's not see-through glass, but it's opaque, and so if light hits it, you can have a little sensor that goes, "Hey, light hit me," and so they can use fiber optic cables to go, "Ooh, I saw lights." That's the only way you have light in a dark tunnel is if something excited it, caused light, and it goes, "Aha, I found light." Okay. Neutrinos on the far left side, these blue boxes, those also, this is what was cool, is they have these sensors that go, something was here, something was here. And they have them lined up in such a way that when it hits it, they can backtrack it and pinpoint it very accurately. So they don't have these things just like stacked like wrestling mats or like gymnastics mats or tumbling mats, right? Because then if it hits one, it hits another, it's somewhere in the whole thing. They have them off-centered a little bit so the geometry makes it so they can track it back to a single point, which is really cool. I thought it was pretty cool. When they told me that, I'm like, you guys are so smart. Scintillation we're going to talk about. Muon detector. I have two links here. It's on the thing. You can actually turn your smartphone into it. You ready what you do? My daughter has my phone. Okay. You got to see my hands. Stop sharing. Okay. Okay, here's a smartphone. Here's the camera. It's not a smartphone, people, I know. But you have this camera. Cover it with black duct tape. Okay? Good so far? Will any light go through it? Okay, hold on. Let's try this again. Hi, guys. I just put you in a room that's surrounded by bricks, top, bottom, and floor. Do you see any light?
No, probably not.
Good. There's no light bulb. There's nothing. You're just in there going, this is the dumbest experiment. What's happening, right? And if you were inside there and you saw light, would you be like, something happened, right?
Yes.
Okay, good. That's what's happening in this detector is you have a completely dark room and you see this light. Well, you can do this on your phone. And we call them, I found out, look at this thing. Yeah, it's my pointer. If you download that app, it is not in the Google Play Store. It is not. Uh-oh. Clean up an aisle. Schmear, what happened out there? Oh, Oh, chaos. It's okay. So you literally cover your phone with duct tape, the camera, and then you just leave it out. And what it does is it just takes a whole bunch of pictures and just sits there and waits. And eventually a muon will hit it and excite the sensor on your phone, and it'll say, hey, look, there's a muon. And that's it. Like, you can literally turn your phone into this. It's really cool. Cloud chambers, you can also make those at your house. I highly suggest making one at some point in your academic career. If we were face-to-face right now, I would then make you make a cloud chamber. They are absolutely the coolest thing ever. Okay, you guys ready? Okay, here we go. My father-in-law's outside. He used to fly F-15s. And here's the first question. What happens when you go faster than the speed of sound? You guys know what happens. You have a sonic boom, okay? So this airplane, if it goes faster than the speed of sound, it's now going faster than the sound that it emitted a second ago, and it creates this cone, and it's a shock wave. And you guys would call it, what would you call it? Shock wave. I'm gonna be quiet now. Shock wave, okay? And that's it, right? You're on the ground, you've experienced a shock wave, this huge, massive wave, all right? So we're gonna use this idea, okay? You guys ready for the coolest thing? Say it together now. Chernikov. You guys got it?
Hopefully.
Just me. Yep. Okay. So we need to start with one idea. Since we only do, in physics 1, we don't do light. One of the things that happens to light is when light enters a substance, water or diamonds or cubic zirconium or glass or oil or any substance, it actually slows down. As it goes through air, it slows down a little bit, okay? So there's idea 1, okay? Light slows down when it enters a substance, okay? Well, what happens if you go faster than the speed of light? So let's go sound. What happens when you go faster than the speed of sound? You get a shock wave. What happens when you go faster than the speed of light in a substance? You get a light shock wave. And guess what color it is? There's your hint today, people. It's blue. It is the weirdest phenomenon. You can go to Reed College. So if you go visit Reed College and go to their reactor, they'll do a forced shutdown like this, and you'll see the blue. And it's completely safe. What it is it is emitting particles that are going almost the speed of light. And as they go through the substance, they're going faster than light, and they emit light that is blue. Well, it's really ultraviolet, but it's blue. It excites the water and excites the electrons. And you see it. It's called Chernikov radiation. So guess what they're actually doing when they're doing scintillation? They're literally having super high energy particles blast through a clear substance, and it leaves this little bit of light flash behind it that makes you go, something was there. You know, and that something that's there, you can then look at the light that got emitted, and you can actually know how fast it was going. I have this link here. This is the IAE. I can't say it out loud. How do you say it? Okay. Particles moving faster than light, but I found these guys. It's the International Atomic Energy Association. These guys really care about it, because if you have a nuclear substance in a water thing, well, how do you know if somebody's not hiding nuclear material that's not supposed to be there? What are you gonna do? Dive down there and pick it up? No. Okay, do you know what you're gonna do? You are going to look at the wavelengths of light that are coming off of it. And once you know the wavelengths of light that are coming off, you know what is emitting. This is really cool. And this is why when you see pictures of nuclear reactors, the water looks really blue. This is it right here. If you then look at it and you get the exact wavelength coming off, you know the energy of the particles, and then you know what the particles are. Isn't that cool? So the folks in Argentina, oh my gosh, things are moving too fast. We talked about them the other day. These guys right here. That's just a tub of water. Do you know what happens in the tub of water when a particle goes through it too fast? it emits a little flash of light, and then a little sensor inside goes, hey, I saw light. Okay, this would be like you guys hanging out in a swimming pool that's covered, it's completely dark inside, and then all of a sudden you see a flash of light. Would that freak you out?
Yes.
Cool. Let's talk about who experienced this. You ready? First Apollo mission. First guy to go up into space. He's going around. Whenever he would sleep, he would notice, get ready for this, he would notice flashes. Because the cosmic rays in space were running into his eye and causing flashes. He wasn't crazy. He was seeing flashes. He was seeing Chernikov radiation inside of his eyeball from cosmic radiation, right? So, you ready, everybody? If you're the first person to space, do you come home and go, dude, when I was up there, I saw like flashes of light. Would you ever say that to somebody? Do you know why you don't say that?
Think you're crazy?
A, they think you're crazy. B, are they going to let you go back? Because they think you're crazy, right? Oh man, some biological thing going on. Let's not send him back. So guess what he did? He told nobody. And then the next person went to space and he came back and they were just kind of sitting in chairs. And he's going, hey, did you ever like see flashes? And the other guy's like, I did too. And they started talking and they realized, oh, this is a phenomenon. And then they told people. They waited till 2 people saw it before they shared so they wouldn't both get fired. Isn't that kind of cool? I thought it was kind of cool.
Yes.
I have a link now here to it, the AMS we talked about the other day. This is up in the International Space Station, but it does the exact same thing that the Particle Accelerator does in Switzerland and Fermilab and all of them. It does the same thing. And it has these 3 tracker plates. These tracker plates are really cool. They're called TOFs, time of flight. And as something goes through it, it marks the time at which it went through it. And then it just does basic physics. And you go, well, if I hit this one at this time, and this one at this time, and this one at this time, guess what that means? You now know how fast it's going. And then you can actually triangulate it and know where it comes from. And so then they can know this is where it comes from in space. This is the coolest thing, okay? The magnets, the only servicing they've had to do is on the magnets. And then we also have a helium vessel to super chill the magnets. And so that's actually, we have to have people in the International Space Station to work on this. We cannot just be like, it's all good. We literally need people up there. We need the ISS to keep doing particle physics. The event that they saw and tracked was massive. I was reading about it. Cool, we're gonna leave that. I think we have a brief introduction. Brief. Okay, you guys ready to play a game?
Yeah.
This is the path of a single particle. This is the CMS. We heard, his name's Peter. I'm gonna show you his credentials in a second, but the collision happens in the middle. And then this is literally what happens as particles leave that collision. This first part is it hits silicon, and that's where you see your charged particles. The other ones is you actually see protons coming, and then they decay, and you see what they're made up of. Calorimetry is heat, okay? Some of them go through all this stuff, okay? They go through it. And then they get out here, and then what would they do is they track the heavy muons and they have magnets bending it the other way, and then they can track it backwards. And it is super cool because it's just a mathematical game. 7 meters is about 22, 23 feet. This is 23 feet away from the center. It's huge, it's massive. And every one of these sends a little bit of information. Okay, so this collision right here, right? Every 25 nanoseconds, multiple collisions are happening. Sometimes it's like 7 to 100, okay? And so all of them happen every 25 nanoseconds. All of that information has to be processed before the next collision happens. All that information has to be sent off to a computer before the next collision happens, okay? So what's happening, guys, is by them doing this, are we getting better at computing? Are we getting better at timing? Are we getting better at sensors? Are we getting better at superconducting wires? I mean, because they need this to be so accurate, fiber optics have gotten better because of these guys. Because in that sensor, every one of these things has to then send fiber optic information back in a very, very small space. So if we look, don't get sick. You will be, oh shoot, you're probably all sick. See that thing? Look how massive that is. That's Alice, bad example. Here's the CMS. Okay, see the dude down there? All of these sensors go all the way around it right here. It's really cool. You guys want an engineering story?
Yeah.
Okay, engineering. Okay, this is a 360 video, like a VR goggle thing. But you see that little tube in the middle? Okay, if that tube was made of like lead, it would capture a whole bunch of the atoms. Okay, so let me show you periodic table. Okay, think about if you were going to build a tube. You were the engineer, and you're like, "Hey, I want to build this tube. Check this out, guys." Right? Okay, let's talk about the lightest atoms that take up the least amount of space. Hydrogen, that's a gas, right? That's not going to work very well. Helium, it's a gas. It's not going to work very well. Lithium, highly explosive. Is that a good one to use? What's the next atom? Beryllium. And so they literally built this thing out of super lightweight beryllium. It is a very small atom with a small nucleus, and so it doesn't block much stuff. Now, watch. What if we made it out of steel or iron, right? If we made it out of iron, it's now a bigger nucleus. Oh, let's build the thing out of lead. Okay, well, I can't even find lead. Where's PB, people? There it is. Don't need it, right? It's a really big nucleus, and so it's made of beryllium. So guys, where do you buy beryllium? Beryllium. Where do you buy beryllium? Beryllium mine. This isn't actually a fascinating thing. Ooh, we actually have beryllium now. The US has more beryllium. We used to not have a supply of beryllium. And so it was interesting. We met the guy who was in charge of the engineering group, and they had to go get beryllium. And they had to go basically into an old Eastern Bloc country. I forget which one it was. It was one of the stands. And they had to go buy beryllium, millions of dollars worth of it. And I'm like, okay, that's cool. And he goes, yeah, we had to tell them how to mine it, how to get it, and how to get it to us. And I'm like, that's really cool. So okay, you have all these collisions that happen. And then every now and then you see an exciting one. Okay, so when these collisions happen, you see all of these just kind of random stuff coming out, right? Random stuff. And then I want you to key in right here. Do you see that little blip? How it's a little bit higher. You kind of seeing that?
Yeah.
Okay. This is literally all they do at CERN. Okay. The Higgs boson, one of the biggest discoveries we've made, in the last 70 years, is from a graph that looks like this, from about 850 observations. They saw it, roughly 850 times. As they have the detector going, they have more, right? Originally, when they did the discovery, they had 70. Okay. I believe they had 70 samples. And so this little blip is how they found the Higgs. All these other ones are just random. They're just kind of bouncing back and forth. But this is mathematically different. Okay. So here's a way to think about it. Let's say I took high schoolers, right? And I measured all of your heights, right? Would I expect to see, like for different ages, would I expect to see different heights, right? If I did everybody in the Evergreen School District, right, I'd see different heights. But then every now and then you see like a 10-foot or 9-foot dude, and you're like, outlier, right? Or somebody like took human growth hormones as a kid, right? Or I don't know. And then all of a sudden you have this little blip, and you're like, we have something. Or IQs, right? IQs. I see different IQs, and all of a sudden I see a blip. I go, that's something different. Or I'm growing something, and all of a sudden in a certain range, it's whoa, it's super effective, right? Or medicine, placebo effect, right? And then all of a sudden you see a little bit extra. This is what they're doing. Okay, we're gonna play a game. You guys ready to play a game? This is where it gets good. You guys ready? Okay, cool. Oh, there's Peter Higgs. Okay, he was not part of it at all. He theorized it back in the 60s, and then here we go. Here's me sitting in his chair. He wasn't there that day, so I got to sit there. So I thought that was kind of cool, right? There's me in Switzerland sitting in Peter Higgs's chair when they announced it, and everybody in the whole place looked at him and said, "Thank you for, your idea and then your mathematical proofs that went with it." And then they spent basically 50 years designing an experiment to find it. And there's me in his chair. Isn't that cool? I thought you'd like that. It's kind of cool. Okay. And there's Shmir. So just making sure you're watching. And so that's how I know none of you are. Okay, so you guys watching it all?
Yes, we are. I think we're just speechless.
A little traumatized. There's a small Shmir. Okay. There you go.
No, you're not blonde.
Yeah, there's high school Shmir. Okay. That's a solid shirt game going on there. Okay.
What's with the king costume?
Dude, my aunt sent that to me. I was the Tolo king. It's pretty sweet. Look at that. I got a hat. I took it home. I wasn't supposed to. Who cares? Okay. And so one of these plots contains the simulated Higgs boson signal. Can you spot it? So we're going to play a game. Go to joinpd.com and go to DSPDT. Let me make sure it's still the same code. Is that okay? Oh, yeah. We're in. Let's see how many students we get. We're going to actually do this. So just a second. Hold on. Are you okay? Finn? Is that you? You okay? All right, we're good. Whew. Okay, she's good. She's good. Okay. Okay, Gamma channel. So what we're gonna do is we're gonna play with this. Ready? Here we go. I did this experience, I should say, with his name's Peter. Okay, he works for CMS, and he's like, we're gonna do an experiment. Okay, if you have an odd birthday, you're in the group on the left, and so you are the Atlas group. Okay, so you're there at CERN, and then if you have an even birthday, you are over here, and you
like the day of our birthday, the month, or the year?
Sure, I don't care. My goal is just to split you in two. That's all I'm trying to do. So right.
Well, what happens if we all have even birthdays?
Statistically, that won't happen, so we're fine. So, actually, hold on. How many of there are you? Yeah, the odds of getting all even.
We should all pick even just to annoy you.
I will send you all back a grade. Okay, so in the left group is Atlas, the right group is CMS. You are two separate groups on this detector, and your job is the following. The first group that finds it gets research funding. Oh, go back. The first group who finds it gets a Nobel Prize. The first group that finds it gets their research funded for the next 50 years. The first group that finds it gets to be in Switzerland and getting paid by their universities. So are you highly motivated to find this?
Yes.
But if you find it and it's not really it, do you know what happens?
Death?
No. It's like a false alarm. And now all of a sudden, nobody's going to believe you. And you're like, no, we really found it. We're like, you probably didn't. They only get to report when it's statistically significant. And so I want you to guess right now, where do y'all think it is?
What is the code again? The code wasn't, it didn't show that screen.
DSPDT. DS. Are you there now?
No, not yet. DSPDT.
DSPDT. I'm still figuring out how to be a teacher, guys. You guys are laughing again. DSPDT. How's that?
Looks good.
Oh no, go back. Why do I keep clicking things? Okay. DSPDT. Do I have a couple of you in there? The rest of you, you're not in there. We can just talk, right?
Mr. Schmier,
Yeah.
when you say find it, you mean like kind of like an outlier on the graph, right?
Yeah, where do you think the outlier is?
Okay.
Yeah, that's basically what I'm going for.
All right.
And watch this. And if you weren't able to log into joinpd.com, just shout out and be like, I think it's at this number on the bottom.
Okay.
Yeah, that's all. We got a couple. You little punks, you're all doing even. Oh my conspiracy. You, yeah, I got one on
No, yay.
you.
To be fair, my birthday actually is on an even day.
No,
Same here, 24th.
I'm pulling up Skyward.
Yeah, my
Hey.
birthday actually is.
Yeah, I haven't
It's
even.
an even birthday day and an even birthday year, and it wasn't an even
Same.
month, but
I
I'm
don't believe any of you. Okay, so
Pull up Skyward.
I can't
You'll
believe
see.
Skyward on a recorded Zoom session. I'm pretty sure I'll be fired. So
oh, come on.
it's just personal information and bank account numbers. Okay, so
No problem, right?
notice where you guys put it. Are you confident enough to say that is where it is?
Nope.
Right. So look at how many pieces of data we got. See how it says 160 up top. And so we got some data. Okay. You guys ready? We're gonna move on. We're gonna collect a little more data. Now we have I think this is 2,000 runs. I want you now to put another one up there. I think this one you draw. Does it say draw? Draw an arrow. Where do you think it is? Just stick it on there. What do you think? Overlay. There we go. Oh, we got a nod birthday too. Hey! All right, all right. Oh, I don't see any of your names. How exciting. So you guys are feeling pretty confident right there. Feel free to switch to Atlas if you want, if you're not feeling it. Now, here's what's really important. They make sure that these two groups don't talk to each other, because if they talked, then they would have bias. They never shared. They would eat dinner at the same place, but they would never share their findings. So okay, we got some ideas. Whoa, we got big shading on the left there. Okay, here we go. Next step. Okay, we've doubled again. We've doubled the number. Do you feel like it's somewhere? Put an arrow. Do you feel like you're ready to report? Do you feel like you're ready to go to the news and say, look, we found something? Are you confident? Oh, not confident. There it is there we go. See, that's an honest arrow right there, right? Some of you are like, oh yes, I am. Some of you are thinking of that little blip right there, okay? Ooh, that little guy, a little bit of a negative. All right, here we go, okay? We've doubled again. 10, yes, it's time to submit. This is where I think it is. 1, no. What do you guys think? Give me some numbers. We got a couple of you on the high end. No, you can't have a negative 1,000. Oh. Are we ready for summer? Oh, man.
You know you love it.
Can I show you?
It's fun.
This is the last slide. Okay, I'm not giving you a chance to write. Where do you think it is? Because on the next slide, we're going to do 2 times more, and I'm going to show you where it is. Are you ready?
Here.
It's here. On the left side. Watch. As you did more runs, did this on the right flatten out a little bit? Did this straighten out a little bit? Did this little negative that was there go away? But this, statistically, bumps up ever so slightly right here. So this is a little bit extra. And what that means is there's just a little bit more there, which means there was a particle that existed and then emitted in that range, in that energy. And that tells us, that was the energy of the thing that decayed, because I had a little bit more than that. And a nice spoiler, Peter Higgs said it would be in this range. And mathematically, this actually lines up pretty close to what he theorized back in the 60s. Isn't that weird? This is about 5,000 runs. Not that many. Okay. I mean, 5,000. I mean, hundreds of thousands at this point, but like, right? And you don't have huge, massive amounts. This is what's weird is all of these collisions are happening, but not that many produce what you want. Oh, nobody wanted this last time. Do you guys want to talk about damage? No? Okay.
Sure.
No, you don't have to. No, we're moving on. You don't want to talk about it? Yeah, let's talk about it. Guys, you have a particle accelerator. What do you do with it when you're done? If it runs into the side, they wanted to see what it would do. This is what a little packet of protons did. Oh, okay. Last night I was trying to think of another way to drive this home. You know the little helium tanks? A little bit of helium? Get a little tank like that filled with hydrogen. That's how much they use in a year for these protons. It is very few protons. You could fit it in a little canister of air, okay? That's all they use. Back in the 70s, they're like, let's just run this thing. This is the best picture I found. That's just what they did. It just, whoop, right? So now you have this particle accelerator. You're all of a sudden done, and you're like, where do we send them? Guys, where could you send the particles when you're done? What could you do?
Space.
Problem is it's underground and it's fired horizontally, so then I'd have to bend it upwards and shoot it to space. Good point, though. I like it. These are good guesses. Yeah.
Do they put it in the ocean, or is it like in the mountains somewhere?
Yeah, couldn't you just shoot it in the ocean? That makes sense, right? Problem is they don't have any water near it. They don't want to have water near it. I like it, though. Good. So
What about all the fish?
fish, yeah, I mean, you'd end up killing a couple fish. Not many. Just being honest.
Do they put uranium in the ocean for nuclear energy?
There's two ways to answer that. If you can make sure it doesn't move, it's a great idea. But when you put anything on the ocean bottom, there's huge currents, and so it's going to move. Okay, so that's an issue. But it is actually a really safe spot because that radiation won't reach us. So it's actually a really safe spot to put it. Problem is the thing that you store it in ocean water will corrode.
Shoot it at people.
Okay, one is, could I have this beam then go to a hospital and they could use it to treat people?
Yes.
Yeah, that's one thing they actually do. Good job. You know what the other one they do is they fire it into different materials and then it collides with the atoms and makes new atoms that are radioactive. They then put them in little bottles and bring them to the hospital. This is how we get radioactive material to put into people's bodies. I actually had, it was a short half-life. I had to ingest it so they could see me under a CAT scan. And so they actually will use the particle beam to transmutate particles, and then they'll use those particles for different research on people. So I was one. They wanted to be able to see inside my brain, but they couldn't see it very well. So they injected me with something that was radioactive, and then they could see me just fine. Maybe that's why I am.
That's insane.
No, it's really cool, and it's cool. Anybody who has a CAT scan, anybody with braces who has a CAT scan has to usually. That was my issue. Is my braces? They just screwed up the resolution. So that's some sweet braces. So let me show you what they do. One, there's two ways to stop a beam. Just let it hit the sidewall. If it hits the sidewall, it goes through the sidewall. All of the liquid hydrogen evaporates and causes a huge explosion. You can't go in there because it's liquid hydrogen and it's now, liquid helium, and it's now helium filling there, so you can't breathe. So you can't even go in there and work on it. Super cooled, it would hurt you. It's a vacuum, right? So now all of a sudden it's just gonna crush itself. This is what happened when the beam hit the sidewall, just once. They lost the beam and hit the sidewall, and this is the damage it did. Isn't that
Yikes.
nuts? Yeah. So don't hit the sidewall. Okay. Now, what they do is they actually, to dump it, they don't dump it into metal because metal will melt and off it goes. Instead, they send it into graphite. But if you send it into graphite in the same spot every time, well, you eventually bore a hole through it. I think you're saying yes. You just don't want to hit unmute. Okay. So you know what they do? they give it a little bit of spin, like a corkscrew. And so when it hits the graphite, right here, go back. When it hits the graphite, it corkscrews into it. And so then that way, when you send the next package in, it won't go to the same spot. Isn't that cool? Remember those concrete blocks I talked about? Do you know why it's so important? When this happens, all of that radiation comes off. The Chernikov radiation comes off, and the concrete blocks block it all, which is really cool. Thought you'd like that. Okay, cool. Okay, maybe not. This is what a picture of it looks like.
That's cool.
Yeah, this is actually, so I mean, right now, let's go there, okay? You can literally go see what's happening right now, okay? This is the long shutdown. Spring 2021, they're gonna open up, bigger magnets, bigger awesomeness. And so you can always go see the beam status, which is really cool. I mean, you could actually, like anybody can go do this. What else do you wanna know? Let's do CHS. On Act 3, see it's going down, right? So there's no particles in it right now. I mean, literally, we would sit there at lunch, just being goofballs. You know what we'd do? We'd sit there at lunch, and on the screens, they're off. Beam, right? We would sit there and look at all these, and we'd make comments like, yeah, the magnets are a little weak today. And so, and we would just act like we were like researchers. It was so much fun. We were such dorks. I'm serious, we were. All right, Ray, so what? Okay. I could show you her presentation. I can actually give you her email. You can contact her directly if you want. So just send me an email off to the side and I'll give it to you. But she basically gives a presentation. I don't want to download it, but you can download her presentation too. But she does some pretty cool stuff. Let me open your eyes to this. So particle research, right? So X-rays, you usually use X-rays, right? And then a detector, okay? This is the original X-ray. You have an X-ray source that emits X-rays, and you have a body in between something that's like film, right? And then you just go and develop the film and you look and you can see inside of people. Isn't that cool? That's all it is, okay? What is the pattern recognition system? The doctor. The detector is film. The object is a person, and the X-ray source is a source, right? So we're gonna take that idea and just keep doing this. So CERN from a physicist standpoint is, I have the particles that I'm going to detect. I have something that will accelerate them, and I have this huge computing system to discover the Higgs boson, right? So we have this infrastructure built to discover this thing. Oh, I can't wait to talk about that. That'll take like 2 minutes, but that's gonna be really cool. Medical. So I think it was cool. She just turned this on its head. She goes, well, this is how we see it. Yeah, you got detecting particles, large computers, accelerating beams. We're gonna use all this stuff to try to solve our issue with cancer. We're gonna figure out how to stop cancer, right? So first is accelerating particles. Second is detecting particles. The third is using computing to analyze that. Before, we used to, right? We had an accelerator, X-ray source. We had a detector, right? And then we had something that did all of the processing. It was a doctor, okay? And the object, right, was the whole person, but we were trying to look at certain things inside of them, okay? Now, I thought it was great. And she's like, well, here it is. It's a big issue. 3 million new cancer cases in Europe in 1 year, nearly 15 million cases in 2015. The number keeps getting bigger, and they expect 25 million in 2030. There's about 8 million deaths per year. And so she has one role, is she takes physics and thinks about how can physics address this problem? How can I take something I'm learning in physics? How can I take something we built for physics and take all of that technology and innovation and patents and transfer that to thinking? Oh, let's see. Did it finally download? Let's see. Does anyone know where it downloaded? Download it anyways. You know I meant that. 129 megabytes. That's enough. I'm ready to talk about antiparticles because that's just going to mess with you. I'm actually really excited for you guys. I kept this link here on purpose so you can see her name and see her email. She's like, yeah, you got a high schooler who wants to talk to you, a college student wants to talk, just let me know. So she, I want to get you here. Madam Curie, cool. No. I try not to steal everything she did. I want to give her full credit for it. She was awesome. So you have a couple different things, right? It doesn't do you much good just to find it and then not do anything about it, right? But then it's also, how do you only impact them a little bit? How can you find a way to only impact one little spot on the person and not their whole body? Because x-rays impact everybody, okay? So, and I think the way she said this is like, find the tumor, address the tumor, whole tumor, and nothing but the tumor. And I'm like, you're funny, okay? She's awesome, right? So you have two things. One is you have to detect it, okay? So at CERN, they're all about particle detection. Well, imaging is the exact same thing. It's particle detection. We're going to show you what a PET scan is, okay? So here's a detector on the left side at CERN. Here's a detector on the right side inside an MRI machine, or this is actually a PET scan, okay? So let's talk. I don't want to do CT. I want to do, give me there. Where's it? PET. Yeah, PET. Okay. PET scan. Okay. So what you do is you put a radioactive substance in a person, and when it decays, oh, I gotta draw on this thing. We gotta draw. We gotta know some physics. Okay. So you put a radioactive source, and when it decays, it'll emit an electron one way and a positron the other way. I think you put a line over the top. If I got that wrong, please don't judge me. But it's a positron, okay? Not a proton. It's an electron that's positively charged. What literally happened was an electron came out and an antiparticle came out the other way. And these exist, okay? I've been in a PET scan. Let's not raise our hands who's been in a PET scan, but you probably have somebody in your life that's been in a PET scan. You literally are there, and they put a radioactive source in you, and out comes an electron one way and a positron the other way. And guess what they do? So if here's your brain, and let's say you have a tumor right here, right? Tumors pull in glucose a lot faster than the rest of your body. And so it's pulling in more of the substance they injected into you because they lace glucose. And then guess what happens? Out comes an electron here and a positron here. And then what they do is, if you have a sensor over here and here, they'll see a little dot here and they'll see a little dot here. And all they do is connect the dots. And they go, it's on this line. And then it emits again. And then they have sensors here. And it connects the dots. And all it's doing is seeing where the two things hit, and it connects the dots. It connects the dots. It connects the dots. It connects the dots. And eventually you see this. See the body on the right side here? You literally see this glowing spot right here. That glowing spot is where glucose is getting absorbed a lot. And so you're seeing the positron electron emission coming off of it. That's it, right? Same with the brain, right? You can now map the brain and see what are spots that are consuming glucose faster than the human body does, because tumors are ferocious. They just eat, and they just eat and burn through sugar. And so they can find them. Problem is so does your bladder, is where a whole bunch of this goes. And so it's really hard to see around your bladder. So PET scans have a limitation. They're not good around your bladder. They're not good around, what's another part that, oh, your heart. also has a lot of sugars that it's pulling in. So there's a couple spots in your body where it's hard to use it, right? So that's one tool in their toolkit. Okay. Then you have CAT scans. You'll hit it with X-rays, and then you will see what comes through the other side, what got absorbed and what didn't. And then they'll know what got absorbed at different spots. This is a 3D X-ray CT scan of a human wrist with a watch on. Do you see it all? They were able to know what was tissue, what was muscle, what was bone, what was marrow, what was metal. Isn't that crazy? Isn't that cool? Okay, just me. Okay, that's cool. So PT, you inject somebody, cool. How it works, keep learning about it, super cool. So see the bladder down there? So the bladder, it's really hard to identify things around the bladder. And so it's one of the issues they have, okay? They know that, okay? So you got PT scan, normal brain, right? Somebody with Alzheimer's. So this is her slides that she shared with us. She goes, the Alzheimer brain, somebody with Alzheimer's, it processes different. And so different parts of the brain are working differently. So they can use PT scans, okay? So notice what this is. Now you don't have to be claustrophobic. Like there's some people who you can't put them inside there, or it's going to cause a lot of issues. So they don't have to anymore, okay? Breast cancer detection, super powerful what they do there. So yeah, all of the sensors, so they'll put somebody through a CT scan and a PET scan at the same time, and they can overlay them and do both. This is all, the field is developing because of what they're doing at CERN. So one will give one picture, one will give the other, and then they overlay them, and you'll see the joint effect. Isn't this cool?
It's really interesting. You said with the Alzheimer brain that just because it processes glucose differently, would that occur then in like, is that how they map other like mental illnesses as well?
Oh, no, I will not make that leap at all. Alzheimer's, I remember, I'm not a doctor, but she has this, and I remember her talking about it. It's just the brain processes it different. And so this is one of the things they've observed. So they saw a symptom. Alzheimer's patients with Alzheimer's would have certain symptoms, and then they did PET scans and they saw certain things, and they started to try to draw conclusions. And then they look at people who, right? So I mean, if somebody has an accident or something, and you lose part of your functionality, they can then do a PT scan and see, oh, that means that part of the brain does X, Y, Z. And so brain researchers, we don't know much about the brain, but we are learning more about the pieces and how they work and how they work together. I'm hesitant to say any more, okay? Have you noticed yet that this thing is always in a circle, okay? Because the sensors, where are the sensors, right? She got a good picture, don't get sick. Right here. The cover thing, so you go sliding in and you hear this whirring noise. It's because the sensors are flying around you at geez, how fast is the PET scan? How fast does MRI rotate? I didn't do my homework. I'm not going to get a straight answer. I forget how many RPMs it is, but it goes really fast. And as it spins around you, those sensors are just picking up particles at different moments in time, and then they're tracking them back. All these cords, all you're seeing is that's just sending information off. That's all it is, okay? But these little sensors, those are the sensors. And so they slide you in and out to see different slices of you with the sensors. That's it. Isn't it cool? So I have that there for you because I'm really, she's the coolest, right? And then let me introduce you to somebody. His name is Michael Doser. So here's me outside of his fun factory. But he was talking about some different things we could do with antimatter. And I think it was fun is he was really honest. He gave us these three things. All right, look inside the body, feel for spaceships, or cure cancer. And it was just like, let's talk about it. And you're like, okay, right? And what he started talking about with us was really cool. I want to share. I think if there's a takeaway. I think it's this. Let's see. Let me get my pen. I can write easier. Let's talk about damage, because last thing you want to do is try to remove a tumor, but then do damage, right? You want to do the least amount of damage as possible. Well, let's talk about this. So this is the graph that we're going to build right here. So let me do black up here. So here's a graph of it's basically a way to say it is like damage or potency of a particle, and then this is going to be depth. Okay. So let's start with an X-ray. Okay, we're gonna make an X-ray black. I don't know why. As it goes into your body, right? It runs into particles, and now less goes through, 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 less goes through. And this is gonna happen to all photons. So X-rays, lights, infrared, you name it. As it hits your skin, some gets absorbed, but some goes through. So right, I'm not gonna do this to Michael because no. But let's say here's schmear, and you want to treat something inside of me that's right there. If you bombard me with radiation, all of this gets impacted also. So then you shoot me this way with radiation. So all of this gets impacted. So now you've impacted a whole bunch of me, right? So that's an issue. So, ooh, score. May I have the back patio? Sweet. Focus. Okay. Switch. No. No. Oh my gosh. It is so nice out. I haven't been outside yet today. It's beautiful. Okay, so he's got some cool TED Talks I have linked here. So let's do another type of radiation. Let's do X-rays, radiation. But now let's bombard, like let's shoot something at it, right? What's weird is if you shoot a proton at something, it'll actually pass through it and it'll have very little damage. But then when it gets to a certain depth, when it gets to a certain speed and it slows down enough, it dumps all of its energy in this peak. And then it doesn't hurt anything else beyond that. So if you got this thing fired at just the right energy, it'll tunnel to a certain depth. So let's say here's me, and you want to treat this thing right here. It'll go through and have very little impact. But then when it slows down enough, when it gets here, it collides. It's like a little freight train, right? And it collides with it. So that's a proton, okay? Well, what if I used a carbon atom? Carbon atoms have bigger nucleuses, right? Protons just have one little thing. So if I send a carbon atom in, and it goes through, and it doesn't impact, and then when it gets here, and then it collides even more. So now think of the DNA of a tumor, or the cellular properties of a tumor, and now all of a sudden you are colliding it with these little freight trains that don't release their energy till they get to a certain depth, right? So this is where he comes into the story, okay? So he deals with antimatter. And man, seriously, you gotta watch all his TED Talks. So if I take an electron and I take a positron and I collide them, you guys want to know what happens? Out comes light. They disappear and light comes out. Isn't that crazy? Like, and this happens all the time. If you take a particle and you take an antiparticle and you run them into each other, they annihilate, and what comes out is, this is my symbol for gamma, for photon, for light. This is all this guy does, okay? He is studying these antiparticles. Byproduct is cancer research and an ability to treat cancer, okay? He is a theorist. So what does he really want to do? He really wants to understand antiparticles. Okay, that's what he wants to do. But a byproduct of the stuff he does is we get more accuracy. Now here's the thing. Here's schmear. Here's the thing you want to treat. If you bombard this with an anti-electron, or you bombard it with an anti-proton, so it's a negative proton, negatively charged proton. Is this weird yet? Yeah, it should be. Guess what happens when it collides with it? It tunnels. It hits. But when it hits, what happens when a particle and an antiparticle touch each other?
Light.
The charge cancels?
The charge cancels, and they annihilate each other, and they turn into super high energy gamma radiation. But guess where this is? You've just released gamma radiation inside a tumor. So as it goes out, guess what it does? It runs into more of the tumor. And so you get this spike of energy that's even more. This is a byproduct of his research, is anti-proton therapy, negative protons. And that is the coolest thing. And so I got to experience that. He quantized it as 4 times. I don't know how it's 4 times, but it is. And I'm like, what? His current project is this. If you shoot a proton on Earth in a vacuum, it'll fall like a projectile and hit a target. Do you know what his current project is? This could literally be in your lifetime. Ready? We're going to fire a anti-proton, and we're going to see if it also falls at 9.81 meters per second squared. We don't know. This is actually a question we have. Do antiparticles follow the same physics that every other particle in the known universe does? Is that an interesting question? The other way.
Sorry, why wouldn't they?
See, there it is. I think that's a great question. It's a really good question. But let me ask it different. So Evie, we're going to come back to that. Okay. So one is, I'm with you. It should, right? Why wouldn't everything that's an antiparticle just have the exact same properties as a particle? Okay. But we don't know. Why everything obeys the same is a question too. It's a great question of why do all particles, why are they affected by gravity the same? I think it's a question, okay? And we know very little things. And there's also another thing. Remember that picture I showed of our standard model, right? You've got, hey, I know what an electron is. Hey, what's the rest of this? That's light, right? And you have all this stuff, right? And so you have all these different particles. Well, all of those particles have antiparticles. Okay? And the question is, do all the antiparticles follow the same as this? And so this is a theory that people are on both sides of this. It's called SUSY. Supersymmetry, and it's the question that physicists are looking at, because the data that we got off the Higgs, so there's 2 different models, and they expected it to fall into one of these 2 numbers, the Higgs, and it was right in the middle, and it bothered theorists, and so they're like, that means there's more physics out there that we don't know. And so we have a model right now that's the standard model. We have a model about antiparticles. We have a model that we don't know it's true, but you know what? A lot of people think it's true, and there's a lot of strong mathematics behind it. We don't know, though, because the Higgs is not exactly one or the other in both of their models. And so it's exciting. We don't know. And so he deals with that, okay? The other great idea is to use this is fuel for spaceships. Because if you take a proton, which is just hydrogen gas, and you take an anti-proton, so an anti-proton, I always forget how to write the symbol. I think you just do a line over it. It's been a while since I had to. If you just have them collide, huge amounts of energy come off, and you can use that as propulsion. How do you hold this? Because as soon as you hold it in a canister and it touches it, it blows up. So you don't want that. Okay, so no soup for you. Okay, so there's his TED Talk. Guy's super rad. There's me. There's me. There inside. Alina is the anti-particle factories accelerator. Is super cool. It's super cool. Okay, there's some of their magnets. Just give you an idea of scale. This is just at Alina, the small ones. They're not big in Alina, but they're huge to me. They're small compared to the big accelerator. And this is what they have over it. That's the concrete to keep me safe. That's very nice of them. Seriously. There's my crew. There's me inside the antimatter factory, just hanging out, you know. There's that. This is an activity I usually do. I would do this. I would make you do it. I'd do it on a piece of paper, right? 130 million unique books in the world, about 400,000 characters in each book. That's like the average page length, right? And so what if I wanted to take every known book in the world and put it on a disk, right? Each character takes 1 byte. How much data is that? You ready? So that's 100. Oh, can I write on this? I hope so. 130 million. That's thousands, million. 400,000 characters each, and about 1 byte each, right? So that's 3, 6, 9, 12, another 2 spaces. So 12, 14. That's 10 to the 14, and that's like 5. Cool. 10 to the 14 bytes. Cool. Do you guys know what? So that is 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's bytes. Cool. How many bytes go into a kilobyte?
$1,000.
Yeah. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's kilobytes. Let's do megabytes. Well, that's a million, so that's 10 to the 6. That's instead of 11, we're down to 8. 1, 2, 3, 4, 5, 6, 7, 8. Ugh. Let's go to gigabytes. So it's another 1,000 for that. So let's do 7, 8, 5. 1, 2, 3, 4, 5. Okay. Now let's turn on the terabytes. So that's 500 terabytes. Okay. And that would be 0.5 petabytes of data. You guys mean a lot to me. Did I do my math wrong? No, I didn't do it wrong. Let's go to my personal Amazon 1 terabyte drive. 1 terabyte. Let's buy a terabyte. You guys ready? That's going to cost you $50. Okay. That's pretty slow though, right? So let's go back. Since that guy's out of here, that guy we're done with. We are here. See if I did my math right. I think I had a 0 wrong. Oh, it's so close. I had a 0 wrong. Sorry, guys. So every single day. So every book in the world is about 50 terabytes. I had a 0 wrong. I'm so sorry, guys. I failed you. Okay. CERN produces about 68 terabytes a day. So these collisions that happen, think about how much data that is. Okay. That's the data that's stored. But if you do that for 365 days a year, you're talking about petabytes. Yeah, right now, currently, we don't have a way of thinking about how much that is. It's 1,000 terabytes. Okay. That's a lot. And it has to be fast. It has to be able to be recorded and then stored quickly. okay? Because the next thing's coming. And so really what we have is all of this data that's coming out of saying, oh, I had a collision. It was this much energy. I had a collision, this much energy. Every 25 nanoseconds as this happens has to be recorded. So have you figured out yet that there's a lot of data, there's a lot going on, and they have to store it really quickly. And then somebody goes, hey, I want the data. Guess what happens? They then don't get to go to the data that's right there. They didn't go and access the data that they store offsite. Okay. This is nuts. How much data they have. So this graph looks at how many terabytes per month, and what do they do with it? And it's nuts. Okay. So guess what's happening right now with the shutdown? They're partnering with Google to do it faster. They're doing Google Fiber to get the data offsite. Now, you're smart kids. Ready? Seriously, you are.
Sure.
Talk to me, Goose.
Oh, what is it? I have to go today early. Sorry.
Hey, boy, I got you, Josh. Good to see you.
Okay. Thank
Take
you.
care. Yeah, I got you. So here we go, guys. If you were to build a server farm to store your data, is it expensive to build stuff in Geneva?
Probably,
You ever
right?
heard of Swiss bank accounts? Do you know what a Maserati is? Right? Ever seen one of those? When I was in Geneva, I saw 5 on one street. Since being back in the US, I've seen 0. Okay. Ever. Okay. They have a lot of money. Real estate's expensive. France, real estate's expensive. So you know what they did? Remember how they're a conglomerate of countries? Where did they put it? Is it in Poland? Belarus? They literally built a fiber optic cable that went to one of these Eastern European countries where the real estate was cheaper. It was cheaper for them to put down a fiber optic cable thousands of miles and then have a server farm there. Guys, let me give you an idea. Ready, watch. This is where Google puts a server farm. You ready? You know where they put it? The Dalles. Why? Because real estate's expensive by Portland. Why the Dalles? There's a dam, cheap electricity, cheap real estate, and then people who can work it, they have people who need jobs. So they put it out here. Same with CERN. They said, where are we going to put our next server farm? And they decided where to put it was in a country where people needed jobs, and there's cheap electricity, and done. That's it. That's all you do. Isn't that crazy? So CERN, lots of cool stuff. Guys, this is an introduction to all of these ideas. This is not saying that we understand it all, but instead we're just saying, hey, here's an intro, okay? Someday, if you go become a math or science teacher, you have to do this program. Promise me. If you are ever in Switzerland or in France, take a day, go to CERN, go on a tour. If it's shut down, go. You can go down in the tunnel. Okay, you need to go. You need to experience it. It is unheard of. Okay, so there we go. There's particle physics. I'm going to be getting together
Does
with
it
Mike.
cost anything to go to CERN?
What?
Does it cost anything to go to CERN?
No, it's 0. They actually paid me to go there.
Oh,
Do you want to know why?
because you're a science teacher?
Yes, and their simple logic is this. We want our researchers working 365 days a year. If we send them to go talk to people, they only have an impact on like 20 kids, and they might not even be listening. They might be on their phones. That's like impacting 5 kids. They go, but if we bring teachers and you go back, you might impact 10 kids one year, 5 kids the next year, 100 another year. You might do a camp with little kids another year. And then next thing you know, you are training and inspiring the next researchers. And then they go into the field. They might not even go to CERN, but they might impact the things that are impacting CERN. And so their model is a certain percentage of their budget goes to pouring into teachers. So my friend Michael, I talked to him. I'm like, "You've been here before?" He goes, "Yeah, I've been here before." I go, "What do you do?" He goes, "I bring my students. We come for 2 days. We meet some researchers. We go in the tunnel. The kids come back. They think it's the greatest thing ever." I go, "Does it make them want to go into physics?" "Yeah." So all of the partner countries, they invite the students there. Oh, there's Pablo. There he is. And so, Pablo, he's cool. This is my buddy from Jerusalem. He's cool. He is from this guy right here. He's from Philippines. No, he's from Philippines. He's from Thailand. She's from Austria. Her and Jeff just talk the whole time. It's hilarious. There's Cecilia. She's in Argentina, inspiring the next generation. These are my Italian friends. They taught me how to teach in a quarantine because we started meeting with them, like what's working, what's not. They were super cool. So great bunch of people. So if you ever travel to these countries, let me know and I'll get you connected. They're really cool people. There's Ben. He's the most British person you'll ever meet. He sounds like he's from the royal family. You got to go. Super cool group of people. Super, super cool. So there you go. Travel the world when we can. Okay, I'm going to turn off the recording because